Thank you, and thank you for the warm introduction. Hey, I'm delighted. It's a pleasure for me to be back on campus. Last time I was here was over 5 years ago, and this campus grows leaps and bounds, and of course, as a consequence of that, you circle around for half an hour and trying to find a parking spot. It's great to be back. So thank you for again inviting me. Ashrak asked me to give like a half and half talk. Half of it's about my research and half of about curricular issues, curricular innovation, or what do you do as a chair? What are the things that are keeping you up at night? Type of issue. So I prepared this. So I hope you're all here, and I was told that I have about 8 hours to give this talk. So make yourself comfortable. And so I'll start with the research part. But from talking to some of you, many of you may be more interested in the latter part. So we'll try to get to that as quickly as possible. But oftentimes I get asked. So we're located in Glasgow, New Jersey. Now, where exactly is that? So we're technically in the state of New Jersey, although I am very, very. I would say Glasgow is probably a suburb of Philadelphia, so very, very close, about 20, 25 minutes just outside of the city. I live in an area called West Deptford, and this is the Philadelphia International Airport. It's right across the river, so the planes are passing over me as they land, and that's our campus. That's the main campus. We do have a West Campus as well. This Google Earth image was taken roughly last January, February or so. This is our building still under construction. Then we used to be in this building. We ran out of space, and the good people of New Jersey did a ballot initiative and gave us funding to build our second building, and the ECE department moved to that. And the university has been growing leaps and bounds. In 2001, when I joined there, it was about 6,000 students. Now 18,000, so it's in about 15 years it tripled. Most people don't know about the school, so I thought I would say a few words about it. It was founded in 1923 as a teacher education school. It's Glasgow Normal School. For a long time, it was known as Glasgow State College. Most people don't realize this is a state institution because of the name Rowan. They think it's a private school. It is not. In 1992, an industrialist named Henry Rowan donated what was the largest gift to a public institution, not even a university at the time, and that amount was $100 million. Henry Rowan had two conditions for that. Renaming the institution was not one of them. In fact, he did not ask for that. He asked two things instead. One, he said, I want a college of engineering. There was no college of engineering in southern New Jersey, and he being an industrialist, he was having difficulty recruiting engineers. And he said, and not just any engineering. I want the best goddamn college of engineering $100 million can buy. And by the way, how that happened was the Glasgow State College then was trying to raise money for scholarships. So the development person went to this Henry Rowan and said, we need some scholarship money. Would you please give us $3,000? That was the amount he asked. Henry Rowan said no. He said, I can't deal with these things. And so he was actually dismissed. The guy went back. He said, well, I understand you can't give $2,000, but can you please give at least $2,000? We're trying to raise some money for scholarship. Henry Rowan said, no. Our development person did everything that you should not do if you're trying to, raise money, right? He goes back for the third time asking for, you guessed it right, $1,000. And at that time, he said, well, enough of this. Okay, I'm not going to give you $1,000, $2,000, but what would you do if I were to give you $100 million? An amount so unheard, so absurd, higher than the total budget of the university, that he said, we'll do whatever you want us to do. And that's when he said, I want a college of engineering because there was no college of engineering in southern New Jersey at the time. That was his condition number one. Condition number two was he had a multinational company called Inductotherm that makes industrial ovens. And he said, every one of my employees, I want their dependents, should they choose to come to this institution, to have a free education. And we said, sure, come, no problem. Later we realized that, I mean, there was so many impact of this gift, and this is just one of them. Up until then, that school was a small commuter school. After this, we started having international students coming in, not because they had heard of the name before, but simply because they were, in fact, dependents or sons and daughters of employees of inductor term in various countries, including Turkey, where I'm originally from. And so that was just one of the. Now, Henry Rowan was not a graduate of Glasgow State College. In fact, he was a graduate of MIT. So people asked him, like, why did you give this amount, this unheard, dinky little, what appears to be slightly more than a community college at the time? And his answer was is actually quite interesting. It's one word for the textbooks. And he said, had I given this money to MIT, it would have made very little difference. Would have made very little impact. I want this to be transformative, and transformative it has become. So that was in '92. The College of Engineering officially opened in '96. First graduates in 2000. I joined in 2001. At the time that I was considering applying and going there, I had very many distractors. They said that's a career suicide. But I did. And a lot of funny things happened along the road, along the way. The university opened its first College of Medicine in 2012, and in 2013, among many things Chris Christie did was gave us a second medical school. So Rowan is now one of two schools in the United States that have not one but two medical schools. One of them is allopathic, the other one is osteopathic medical school. In 2015, we started, in fact, it was my initiative, once we obtained the research university status, open a PhD program, that's just started. In 2016, the university was ranked number 18 in the Northeast, and the college was number 19 among institutions that offer bachelor and master's degrees. So I don't know if I should say I'm happy or not. That ranking will probably drop to 70, 80, 90 in the next couple of years, because we will no longer be in that category of the SMS institutions. And then, of course, Rowan will not be compared against schools like Iowa State and MIT and things like that once you get to that. But the university grew, as I said, dramatically. So did the College of Engineering and the ECE department. So our enrollment quadrupled in about 6 years since I've become chair. We moved to this new building. The third floor of that building is now ECE. And just recently, the university changed its Carnegie classification to a doctoral university. So that's the brief history.
Total enrollment is 18,000.
Total enrollment in the university is 18,000 now. That's total headcount. That was about 6, 7 when I joined it.
College, total college is
the college when I joined was about 400 students. That was the entire College of Engineering. We were a small boutique school. Now the College of Engineering is about 1,700. And the ECE was about 80 students. Now it's 400. And our faculty size did not quadruple, I must say. And that's a challenge. All right, so let me, I don't know how many of you are here for the research part of this talk, but I'm going to try to go through this at breathtaking speeds so that I can get reasonable of this done. What I'm going to talk about is a topic that we call learning in non-stationary environments under extreme verification latency, and I'll explain what that means. And learning in a non-stationary environment is a machine learning problem where you're presented with a series of data stream, if you will, and it's such that the underlying distributions of that data change over time. Okay? So what you have trained your system previously may no longer represent the underlying does not represent the distribution anymore because that has changed. So there are many examples of this. I'm not going to read all of them. But anything that changes over time, financial data, energy pricing, energy demand, strategic game playing, recommendation systems, these are all examples of non-stationary examples. What's not a non-stationary example? And there are lots of those as well. Character recognition, optical character recognition is not a non-stationary problem because the general structure of the letter A or the letter K does not change over time. So we call it non-stationary environments, but it actually comes under a variety of different names. Different people call it slightly different meaning, but concept drift, domain adaptation, inductive learning, transfer learning, covariate shift. These are all terms that have been used to represent this area. Each of them, every one of them makes slightly different assumptions on the underlying data distributions, whether the posterior distributions change versus the likelihood versus the prior, and so on and so forth. But more or less, they all have the premise of the data characteristics that you had previously are no longer the data characteristics that you have now or in the future. There are a few types of common approaches for this. Those who work in domain adaptation may be more familiar with instance weighting, importance sampling, distribution matching, or changing feature representation so that the new features represent the current environment better than the old one. Or ensemble-based approaches where you, instead of having just one classifier, you have a series of classifiers, and you keep adding new classifiers to the set as new data come in, and you weigh those classifiers depending on the underlying data distributions. Much of these require that you have sufficient labeled data to be able to train. So, and that's supervised learning. And the problem with supervised learning is it is costly. It's costly because it requires human annotation, and let's just face it, you, the human beings, are expensive. Okay, so it takes a lot of money to employ humans. So the general solution in machine learning for this is what's known as semi-supervised learning. So you have some amount of labeled data and possibly lots of unlabeled data, and then you try to make do with that. But if you're learning in a non-stationary environment, then this is even costlier because you need not just labeled data at one point in time, you need labeled data at each and every time step that comes afterwards. So our approach to this was adapting semi-supervised learning approaches so that they can in fact learn in this dynamic environment. The algorithm that we came up with is, I don't want to call it algorithm, it's more of a framework, is composed. It stands for compacted object sample extraction, and then that phrase will make a little bit more sense when I explain the algorithm. So the non-stationary environment itself can come in a variety of flavors. So here's one where you have regularly labeled data. It's non-stationary. You receive data over time. There's one batch, there's another batch, but in each batch you receive labeled and unlabeled data. And that's nice, and it works for our algorithm, but it's not practically very common. It requires labeled data at each and every one of those time steps. It is possible that the labeled data that you get at any given time step is really the labels of the data that you had previously seen at a former batch. So that gives rise to what's known as a test then train approach. So you have a verification latency, meaning the labels become available to you at some point in the future, but that latency is usually small. You have the sporadically. Every now and then, labels become available to you. You start with some labeled, unlabeled data, and you get lots of unlabeled data. At some point in time, you get the labels for the data that was previously available, but now that latency is much longer, and then you have to figure out a way of tracking this. And then there is the extreme version of this scenario, and that extreme meaning the labels are never available to you. That means that you start with some labeled data, and then from then on, all the data that you get, that you receive, are all unlabeled. And mind you, remember, the premise here is that underlying data distribution change over time. So the data distribution here is different than the data distribution here, but you no longer have labeled data to help you track that. Okay, question?
I'm curious, you said you were talking about non-stationary environments, but do you assume a model on the non-stationarity, meaning you assume that it does not change too much? Which changes completely.
I'm glad you asked good questions. So what assumptions are we making? I'm going to come to that. In fact, I'm going to make exactly that assumption. So, and then we'll talk about it in a moment. So this is what we call extreme verification latency. It's a misnomer because there is no verification. Right? So it's the extreme verification implies that there is some verification at some point. No, there isn't. So you get your labeled data at first. That's it. That's all you got. So what do you do? And I'm going to do a lot of hand waving here just to give this the central premise of this. But here's what we're going to do. Now I must say that my artistic capabilities were so poor that I actually even flunked art. So my drawing should be interpreted in that context. But with these colorful drawings, I'm trying to represent some distribution. Okay, and an arbitrary distribution. I'm not assuming a specific type. Some distribution. At time t-1, maybe I have this blue distribution, and with the dashed line, I'm representing the central part of that distribution, the high density part of that distribution. Okay, and from time t-1 to t, maybe this moves a little bit in some direction. And I will argue that the core area of the blue distribution still represents, to some extent, to some part of the red distribution. So if I have labeled data from this dashed region of the blue, I can still use it to learn some, not all, of the red distribution. Okay? Or maybe it rotates, right? Maybe it rotates and changes the shape as well. But still, the central part of this, the old red distribution, still explains partially the green distribution. Or maybe it expands or shrinks or does some other bizarre change that I don't know. But in each and every one of those cases, the central part, or what I call the core region or the core support of the original, the previous distribution, still explains some, but not all, of the new distribution. So if I can transfer labeled data from here to here to here to here to here, I can use that labeled data as part of the semi-supervised learning. We originally started with using what's known as alpha shapes. Anybody heard of an alpha shape here before? One. Excellent. That's one more than I expected. And an alpha shape is a generalization of a convex hull. So for an alpha set to infinity, you get the convex hull. For smaller alpha values, you get a tighter and tighter and tighter representation of the data. And so much so that, so this is alpha set to infinity, where it encompasses the entire data, so that's its convex hull. But if you have voids in your data, the convex hull does not distinguish among those. So if you pick a more appropriate alpha, you can get, in this case, the data is the letter P, if you will, to represent the data more appropriately. And the alpha shapes can be obtained through what's known as constructing Delaney tessellations. Once I obtain this alpha shape that represents the data, I like to shrink it so that I get this central core region, or the support of the data distribution. And I do this by removing layer by layer, much like laying an onion. And I take these simplexes outside until I get to a core region, and then I sample labeled data from there. So remember, I start with labeled data. So at time 0, when I start with my original data, I have labeled data. I create this alpha shape around it. I compact or shrink this data to get the core region, and I take the sampled data, labeled samples from there. And I'm going to use that as the labeled data for the next time step. Right? So for those of you who have a photographic memory, this is the entire algorithm in its glorious detail. For the rest of you, for the rest of us, I'm going to use what's most beloved by engineers is block diagrams. Right? So here's how it works. I receive labeled data at time 0, along with some, say, unlabeled data. I'm going to use a semi-supervised learning algorithm to classify unlabeled data using the labeled data that I have. And I'm going to construct an alpha shape for each class, essentially a boundary around that data. I'm going to compact or shrink that alpha shape to obtain the core supports. And I'm going to extract samples from that. Still, I have labeled data. And I'm going to use those labeled data as part of the new data distribution's labeled examples. I get new unlabeled data from then on, but I'm going to transfer these subset of the labeled data into this new environment, and I'm just going to keep doing this over and over and over again. So a different distribution here. Here I have you see some labeled data. The colors blue and red indicate class. Yes, question.
So then the number of labeled samples will keep reducing, because every time you're compacting it and picking a subset and then using it again. And
No, it will not reduce. It will increase, in fact, unless you put a cap on it. But you can choose how many instances that you want to draw at each time step. It will not reduce, it will increase.
So at some point you will attach labels to some unlabeled.
Correct. Correct. Because at each step I'm running a semi-supervised learning algorithm, so all of your unlabeled data becomes labeled. And out of those, I pick a subset.
But before you choose the unlabeled data as labeled data, you have to make sure that you have the accuracy or some kind of a verification done.
Correct. So how certain am I that those labelings that I'm assigning are correct? Yes. So we'll address this issue by the assumption that we're going to make. Yes. So you receive some labeled data, and then I receive some unlabeled data. The black diamonds represent the unlabeled data. Okay? I use a semi-supervised learning algorithm to classify these black so that they're no longer black. They're red and blue. Now they have labels, assuming correct labels. But I don't know that. Okay? And then I create a boundary object around it, if you will. So I create the alpha shape around them. So that I have a core region of this. And I take these samples from those, and I take those samples to be the labeled data for the next time I receive unlabeled data. So here's an example for this. Imagine that, again, the red and the blue stars are your labeled data at time t is equal to 0. The black dots are unlabeled. Okay? I classify the unlabeled data using the SSR algorithm, so they're now all labeled. Okay? I create a boundary object around this. Well, that not really look good. I mean, when I retire, maybe I'll move into modern art or something. So, and then I shrink this, and I say that is my best chance of representing the future data using the current data. Okay? And then I extract samples from this. So these labeled data are now going to use them as the labeled data for the next time step. And the next time, if you remember, this was centered here, it was centered here. But now let's say that they moved. This class moved that way, this class moved that way. I'm going to again use a semi-supervised learning algorithm. And here, the choice of semi-supervised learning algorithm makes a big difference. If you use something like label propagation, then it will propagate these labels as long as they are somewhat well separated. It will propagate those labels here, and it will propagate those labels there, and they will be correctly classified. And then again, and you will see that these things are moving as I go along. Okay. A couple of examples. So here's a bimodal distribution, the red and the green, and they just moved around. And I'll show you a little quick video on how they move around. They move around according to these parametric equations. And let me see if I can do it here. So this can run while I'm talking. You'll see it's actually going to be this red class is just going to move to these two green classes, and then it will split into two. And here I'm comparing it to base classifier. And this is probably the worst comparison you can do if you're going to make an argument for your own classifier, because it's grossly unfair towards our algorithm, because base classifier is running in an entirely supervised manner. It knows the labels at each and every time step, whereas compose doesn't know the labels in the future. So depending on which semi-supervised learning algorithm you use, cluster and label, S3VM, so that's semi-supervised vector machine, label spreading, cluster and label. There is another algorithm called APT, arbitrary population subtracking, that was proposed by some other group. And that's what it looks like. So the black line up here is the base classifier. So that's your gold standard, if you will. That's as best as anybody can do. And then you can see that the algorithm is reasonably well track that, even though there is no more labeled data. It's just propagating the labeled data from previous. Here's another example. This is where I'm going to introduce a new class. It will start with 2 classes, and I'm just going to pop in a 3rd class. And let me see if this video will work. And then so that you can see. So it starts with 2 classes, 2 distributions, red and green. And you'll see that the 3rd one will pop up in blue. And then it's just going to move around, and that's the 3rd class. Okay. I'm providing labels of the 3rd class at the time it appears. And that's the only time the algorithm will ever see labels from the blue. And you will see that, here's again comparing the base classifier that knows the labels at all times to red and the blue, and it actually works reasonably well. Okay. Now, the only condition that we make here is that the drift is limited. So there's your assumption. Okay, well, what does limited mean? Well, it means it's gradual. Let me do some more hand waving. Okay, well, what does gradual mean? Well, that means that there is significant overlap between individual time steps. Okay? That's even more hand waving. What's significant overlap? Well, it's telling your own engineers, right? You demand accuracy and precision. Tell me exactly how much overlap there should be. It turns out, and this was a surprise to us, we don't need any. The algorithm works even if there is no overlap, none whatsoever. So I'm going to skip some of the. We came up with this metric, if you will. We call this drift classification uncertainty. I'll spare you the mathematical description, but all this is saying is that the unlabeled data for any given class must be closer to its corresponding core supports from the previous time step than to any other class. As long as that condition is satisfied, this algorithm will work. So here's a toy example. You have 3 classes, red, green, and blue, and then the black ones are presumably unlabeled data. Now you can tell that this is probably the red class, right? And that's closest to that. And as long as this is really the red class, the algorithm will work. If this was in fact the blue class in the next time step, the algorithm will not work, because these new data is closer to the red support vectors, core support, than it is the blue. The algorithm will have no way of knowing that the blue just shifted all the way here. Okay, so as long as each movement is closer to its class than to any other class, it will work, and overlap is no longer required. Okay?
So,
yes?
Is that something to determine that distance? Is it some clustering, k-mean clustering kind of approach?
So you can do any clustering,
You
really.
compare the centroids of these 2 distributions, right?
Correct. Now, so here's something I was going to skip over this, but since you asked, there is a major flaw here with this thinking, and the flaw is this. This allows me to determine which types of data is likely to work under this algorithm, but this requires that I need to know the labels ahead of time. For me to compute these distances, I need to know the labels of the future data, because how am I going to compute the distances? So this only sets the condition under which the algorithm will work. In a real-world environment, I will not be able to compute this DCU, because it requires that I actually know the labels for the future. Now, I can approximate it using my predicted labels, but then again, how valuable is that, or how valid is that?
I mean, you can say I know the centroids of the known classes of the labeled data,
Mm-hmm.
and then I can apply something like k-means to the unlabeled data with those centroids and come up with clusters that will give you the.
Correct. So I can compute the cluster centers of these, right? But I don't know their labels, so I don't know whether this is really the blue class or the red class or the green class. I can predict that, well, it's closest to the red one, so it must be the red. And if that is indeed the case, then the algorithm will work. But if it were the case that the blue just jumped here, and then this is in fact now red and this is blue, well, then the algorithm will fail in being able to track it. So that is our definition of limited drift. Not necessarily, I'm not requiring that they overlap. It's just that the drift has to be such that the new location, the new distribution is closer to the previous one for each class than it is to any other class. Okay, but in a truly unlabeled environment, I have no way of actually testing that. Okay. Now, I'll leave it with this. The compose is really a framework, and I only showed you one example for the code support extraction, which is alpha shapes. But you can, this is essentially a density estimation problem. You can use GMM, you can use Parsimillos, you can pick your own favorite density estimation algorithm, and this still works. And similarly with semi-supervised learning, you can pick different SSR algorithms, and it still works depending on the data itself. So the algorithm provides a remarkable performance in tracking these underlying changing environments, and works surprisingly close to a base classifier that in fact knows all the labels. Obviously, one can always come up with pathological cases that will make this fail, and I'm already telling you one such case, which is the limited drift assumption. Okay. We worked on several variations of this, fast compose, compose AL, that's AL is for active learning, and so on and so forth. But all of them are based on this general premise. We did write a survey paper on this in 2015. In 2017, this was awarded the Best Paper Award by the Computational Intelligence magazine. So if anyone of you is interested in this field and want to learn more about this, this is probably one of several good sources that you can use. So I'm going to pause here before I get to the second part of this, and then see if there are any other questions on this aspect of the talk.
So what are the application domains? Have you looked at the data sets?
Yes. One data set that we look at is long-term climate change. Okay? And that's where you can see some. And in our case, we actually even look at seasonal changes. Is this able to track seasonal changes? And the answer was yes. Another one is, there's a data set called the keystroke data set. And this is interesting because this is where the user is asked to type a password. And then, does IOC require you to change your password every so often? Yes? No?
Sure.
Yes? Okay. I saw some, I saw ODs, and that's with label noise. And so you then know this. Every time you change your password, the first few times, you may be struggling in typing the password. You're more likely to make mistakes right after you change your password than perhaps sometime. So the problem was tracking and the keystroke patterns of the person, and from there predict whether the person really knows the password or just trying to guess something. And then because that distribution changes as you become better and better and better. So that was an interesting data set. Energy demand prediction was another one, and there's that's a well-known data set among this circle, although at some point later the paper came out showing that in fact was not a good data set for a variety of reasons. Yes?
So, how would it impact the behavior of your approach if you were to use chi-shape as opposed to alpha shapes?
So
Alpha shapes are sometimes not guaranteed to be connected and
correct.
sync.
As a matter of fact, we moved away from alpha shapes altogether, although it helps me to explain it. We're now using just simply GMM, Gaussian mixture model, to estimate the densities. It's faster and it works equally well for that. I suppose you could use, and the reason we moved away from it was computational complexity. Computing those delaying tessellations and all that was just a pain in the neck, except lower. So, yes. Oh, I'm simply mindful of the time, so I'll answer as many questions as you want.
We can take it out. Go ahead.
You had a question?
So suppose your data doesn't satisfy the limited drift model, but you also got new labels instead of just getting the labels in the beginning. Does your algorithm work in that scenario?
Yes. So exactly, and that's the part that I didn't talk about. So the compose AL algorithm is intended precisely for that scenario, where it's not limited, but you get regular or sporadic labeled data. Yes, then it will work. All right, so I'm going to move, and let's see how quickly I can go to this. I'd like to talk about an alternative approach to senior design. How many of you, are there any undergraduate students here? This one, all right, okay. But presumably, everyone here at some point in time went through a process or experienced that's something like it, right? You were asked to do a project during your last year, and that's very common in engineering programs, and probably for a good reason. So bear with me as I go through this little analogy and do the little tongue-in-cheek. So I'm going to start talking about how to make an engineer. That's our main product at colleges and universities, after all. So let's start with ingredients, raw material. Well-qualified cook and support personnel, so that's faculty and staff. You need about 32 to 40 parts of math and science under ABET rules and 48 to 64 parts of engineering. A pinch of general education for flavor. Generous amounts of homework labs and one major design experience. So that's how we typically make an engineer. The actual recipe itself goes something like this. You place all raw engineers in a sufficiently large container. Thoroughly mix with the faculty. Pour in the math and engineering content, slowly stirring, continuously adding homework and projects. Sprinkle general education, as I said, for flavoring. Turn up the heat and boil for 3 years. But be careful, you don't want them burned, so reduce the heat from the 4th year and add a major design experience. Serve hot to industry or the graduate program. So that's essentially our recipe for making an engineer. Well, so that's our primary product, and the customer of this product is the industry or the graduate programs. And they expect and demand a good product, a well-trained engineer. They do give us some feedback, but not much. We ask industry as well as the graduate programs, what qualities would you like to see in our graduates and our students? And you get some such vague statements like, well, we want analytical thinkers who can think outside of the box. How do you... We want team players, problem solvers. And so we're left to ourselves to determine what qualities this product should really have. Of course, I suppose you can ask ABET, and ABET will be more than happy to tell you what they think the qualities of an engineer should be. The infamous A3K. So those of you who are in ABET are well familiar with this. And of course, ABET is changing them. So they updated their list. Starting next year, it will be replaced with this 1 through 7. And if you look at this, it actually does give some good advice. This is ability to identify, formulate, solve engineering problems. Apply analysis, synthesis, engineering design, appropriate develop and conduct experimentation, ability to communicate effectively, recognize ethical and professional issues, and so on and so forth. So, senior design is a time-tested and honored curricular component that addresses many of these qualities. And in fact, it is required by ABET. It could be named something else, like capstone design and what have you. It is intended to provide students with this real design experience. Put everything that you've learned together to solve some real, preferably unsolved problem that shows you that you're able to, because that's what you're going to do for the rest of your career. But here's some of the questions that I pose, and supposed problems that the senior design need to solve, but doesn't. Is it really an unsolved real problem? Or how many of the senior design projects are really unsolved problems? Okay. as opposed to a pet project for a faculty or a student, if the student is the choosing. Do they provide multidisciplinary team experience? One of the requirements for ABET. Does it have real constraints and real deliverables? And how many of those student outcomes does it check off? One of my biggest problems with senior design is, can a real-world design experience be obtained in 1 semester or 1 year? In some programs, 1 semester. In most programs, it's 1 year. And are there enough and diverse set of projects every year, and how many faculty are assigned to these senior design experience? So what we have done is come up with an alternative approach to this that we call engineering clinics. This is our curriculum at Rowan, and it is a combined degree program for electrical and computer engineering. And I've talked to some of faculty here, and I understand that there's a diversity of opinions on whether electrical and computer engineering programs should be separated or together. I'm not going into that discussion other than saying that our studies. There are about 20 out of the 600 electrical and or computer engineering programs out there that have combined. It is infinitely color-coded. My faculty makes great fun of me for creating this, but it serves a purpose here. So you can see, here's the math sequence. Here you can see what's known as the core, double courses, circuits, electronics, electromagnetics, the signals and systems track, the DSP communications, and then here's the COMP part of it. With the exception of electives, and there are 5 of them, everything that you see here is required. Okay? Every student takes every one of these classes. And by and large, you will find these classes just about every engineering, electrical, and or computer engineering program, depending on which flavor. What we're not going to find are these. Right? And that's an 8-semester sequence that we call engineering clinics. That's freshman clinic, sophomore clinic, junior clinic, and senior clinic, which is common to all departments in College of Engineering, plus the engineering clinic consultant that's specific to ECE. Okay. So that's 24 credits of content. So what do we do with those 24 credits? Well, it is intended to replace the senior design. So it spreads the senior design experience to all 4 years, most of the last 2 years. So the freshman clinic is essentially, you already have that. That's fundamentals of engineering, instrumentation, measurement, reverse engineering, what have you. Sophomore clinic is integrated to communication. So it's engineering design, but integrated to technical writing and public speaking. And junior senior clinic is where the magic happens. That's real world research and design experience. And then we add clinic consultant. I'm going to talk about this in detail in a moment, where we add entrepreneurship experience, consulting, professionalism, engineering ethics, and so on and so forth. So we think the junior senior clinic in particular, the last 2 years, is a better senior design experience, but I put the senior in quotes because it's not really just senior, it's junior and senior, right? And it is the one course that does it all. It checks off each and every one of those ABET outcomes. They're all real projects, and I don't mean to use the real as real in a derogatory term, because every project is a real-world project experience. But what I mean is unsolved real-world problems. The projects typically come from industry or externally funded projects, research projects with the faculty. The students can propose their ideas, although they have a very high bar to meet. If they do, we give them $2,500 a semester, $2,500 per project. But it really needs to be a real and unsolved problem. Each project is staffed by juniors, seniors, graduate students, and sometimes even sophomores. So that's the vertical integration part of this. It does provide a mentoring opportunity for the seniors as well as the grad students. And it really works almost like an in-house internship opportunity, if you will. We ask each student to spend at least 1 semester in an out-of-discipline project. So ECE students would have to do something in the mechanical engineering, chemical engineering, civil engineering, biomedical engineering, and what have you. So the key thing here that's different than everybody else is the college-wide commitment to this. All 6 engineering departments participate in this, about a total of 1,700 students, as well as each and every one of the faculty members in the College of Engineering. It's part of their required workload. It does a college-wide protected time. Every Tuesday, Thursday afternoon is clinic time, meaning students don't have any other class. It's guaranteed that they don't have any other class. That way they can all participate across interdepartmental clinics. No labs are scheduled during that time so that all labs are available to anybody who's doing some kind of a design. It really is an all hands on deck, and I really mean all hands. By all hands, all students, all faculty. Okay. So every semester, every department sends many of their students to other departments, so it is really truly inter and multidisciplinary. Where do these projects come from? As I said, mostly development type projects come from area industries. Lockheed Martin is big in our area. Research type projects come from the usual suspects, the NSF, NIH, DoD, NASA, and so on and so forth. Sometimes faculty may propose projects for which they don't have funding, but maybe they'd like to try something and obtain preliminary data to be used for future project proposals, or as I mentioned, student initiatives. So how many projects do we offer in any given semester, you ask? I'm glad you asked. You asked the questions. Give me a guess. How many projects do we offer in any given semester?
In the department or across the college?
Either way. So I showed this slide during our open houses to high school students, and inevitably somebody would say 23, until I said, no, it's actually more than that. Across the college, we offer, well, it varies every semester and all that, but last semester we had 160 projects. That's 160 projects available to any student in our program. And you can see, and some are actually quite interesting projects. I'll show you some examples. Just like Iowa State, Rowan is big on virtual reality, so we do have a virtual reality center, and that's always, they have lots of projects, so they get a lot of students interested in their projects. But another one is, recently is the NASA CubeSat project. Are you familiar with the NASA's CubeSat program? So we got one of those, and the year that we submitted the proposal that we got selected, these were the other ones selected, and out of the 20, you'll see that 4 or 5 of them went to NASA itself. NASA Ames Research Center, Jet Propulsion Laboratories, and some big name schools such as MIT, Lincoln Labs, and then of course there we are. So it was a good list to get associated with. But imagine the implications of a project like this. So the students are designing a satellite, fully functioning satellite that is going to be placed in orbit. Talk about real deliverables and milestones and timelines, because this thing is going up March 2018, whether they're ready or not. Okay.
So you've been chosen.
Huh? It is chosen.
So it is, the payload is called for it now.
Correct. And the payload in this particular case is a memristor-based memory. So memristors, some of you may have heard, circuit component. And the proposal was a memristor-based memory are perhaps more reliable than CMOS-based memory in the cosmic radiation environment. So when I say real unsolved problems, well, that's not building a robot that does something. So I mean that's what we mean. Okay. And of course, imagine the pride the students would have in explaining what they do to their parents or to their sisters. Oh yeah, I worked on a satellite that's going to be launched into orbit next week. What did you do last weekend? All right. So those are the challenges. Not all projects are as high impact, perhaps, but the interesting part of this whole exercise is pitching these projects to students. So the faculty needs to describe the projects and sell these projects to students, and they have to tell what's the project about, why is it important, who funds it, what skills are needed. And the faculty's goal is to sell this project in such a way that the students will choose, because the students get to choose the projects. Okay? So I would these are the projects that I ran last semester, so I'll tell them a little bit about the project and then what are the applications and all that. And then I will sprinkle these images of students going to conferences with me to famous places to entice them. It could be you next time in that picture. And then I'll tell them the next conference that we're going to be going after. Oftentimes, I will put this up, and this is the places where our students have gone. This is my students, my project, out of clinics that they went and presented their work. This is probably one of my biggest.
This is supported by the college for the cabin and so on?
In this particular case, these are all supported by the projects. So in my case, these are all mostly, not all, but mostly NSF funded projects. So.
In REUs. Are REUs? No. These are
Research projects like a career project or any of the NSF divisions and directors. I mean, these are
from your NSF funded research grants. You have come up with some problems, and that you gave to undergrad.
Correct. So you scope the problem, you make it, properly scope the problem, and you run a clinic project on this.
So, in terms of faculty assignment, every faculty is supposed to run
at least 2 projects.
at least 2
Every
clinics.
semester, yes.
Every 2 clinics every
Semester. Everything. But we had this conversation earlier. That's the contractually required workload for faculty. But the faculty has bought into this idea so much that just about every faculty runs more than 2 clinic projects because for them it's free labor. And if you scope your project correctly, you can get an amazing amount of work done by even undergraduate students. And I'm the first to admit that much of the funded projects that I've had and papers written are work of many of these students. The last project I had from funded by NSF is in fact an idea from one of those undergraduate. The non-stationary learning and extreme verification environment, that was an idea from an undergraduate student. We wrote the proposal, submitted it, and got funded.
So would you say that the typical student in your department is capable of doing NSF, REU style research? That they're at that level where they're able to deliver on a properly scoped
It is your job as a faculty member to properly scope and find the students. Not every student can do machine learning. In fact, we don't have a machine learning class at the undergraduate level. Right? So you have to find the right students for your project. I guarantee that every student has some skills. You just have to match the student that have certain skills with the right project that needs those skills. That's really the...
So these trainings, a project would run over multi-year.
Yes, and most projects do. And the students can move in and out. So if you're not a good advisor in that project, the student may leave and go to a different project. And vice versa. If you're not happy with the performance of a student, you could say, I don't want the student in my project.
So how are the students evaluated? Like, do they receive grades for this?
Yes, this is just any other class, right? So they get, and the syllabus says the following: if you do everything we ask you to do in this project, you get a C. Okay. If you go above and beyond that, and say, well, you asked me to do this, but I also did this, and look what I have, and it'll help your project, that's a B. If you say, you know what, professor, you're really looking at the wrong problem. You ought to be looking at this problem instead. And oh, by the way, just to save you time and money, I already did, and here are my results. That's an A. And at least that's what the syllabus says. We're not quite as harsh in grading, because if we were that harsh, these students will not come back to the project. But to answer your question, yes, they get a grade. They get a grade. Okay. The other thing that I do is I tell them what the previous students have done, as far as where are they now, and I'm going to add to this because one of my current students, just after the junior year, got a job offer from Amazon at a salary of $108,000. So, and that's one of my clinic students. The project selection goes like this. The faculty post the projects online with supporting materials like PowerPoint presentations, videos, links, what have you. And the students look at these before they come to the first day of classes. During the first day of classes, they can go and talk to faculty members, ask questions about individual projects, and then they fill out an online form where they rank order their projects as they want, and they talk about whether they had previous experience on this project, why they're interested in this project, what their skills are. and then the students are matched to projects. Typically, they place into one of their top 3 choices. The actual student selection is an orderly and civilized process where the faculty fight over which students get this. Actually, recently we now have an optimization program that automatically assigns students to faculty based on several criteria and constraints. And you guessed it right, that was a clinic project proposed by one of the students who was not placed into a project that he wanted to. And he came to us, I can solve this problem that you're trying to do manually, because that's what we were doing previously. And that was a clinic project. That we actually said, that's a good idea. Let's do that.
So you got A. You got A.
Absolutely. That's what you got it. Okay. And finally, the clinic consultant is just for the ECE students. It's a 2 1-credit courses taken during their senior year, and that's where they learn how to be a consultant, how to identify customers, how to contact customers, how to bill customers, how to handle ethical issues as they may be raised over time. And then we typically ask them to consider out-of-discipline projects, and this is the entrepreneurship training of the program. They fill out a clinical consultant agreement at the beginning of the semester that they are going to provide you with the following services, following tasks. The project managers, the client signs this, the student signs this. At the end of the semester, they say, well, here are the things that we actually completed. The project manager or the client assigns a grade, so to speak, but the actual grade is entered by the course instructor or the person who is instructor on record for that. Okay. And so this is my final slide. So the benefits of this approach is many. For students, it's a real-world design experience, a setting that very closely mimics the outside world or the real world, as a real-world industry setting, if you will. It's a multi-year design experience. It's not just 1 year. It spreads across several years. It does teach mentorship and leadership experiences and skills, and of course, entrepreneurship is part of this. And it's an immediate job opportunity at the sponsor if, in fact, it is an industry-sponsored project. They just gobble up students very early on. For faculty, it's a formal mechanism to engage undergraduate students in research. It's cost-effective and qualified labor. As I said, even though we require faculty to do 2 projects, most of them do more than 2. And in my case, as in most faculty, it's an opportunity to identify strong students to recruit into your research labs as graduate students. Many of the grad students that I have are the ones who came through these clinics. So I had them for typically 3 to 4 years. We did not have a PhD program for the longest time, but we did a lot of research with these students through this mechanism. And for the industry, what could be better? Try before you buy, right? So the workforce pre-trained for their specific type of problem. So there'll be a lot of interest in this. Okay, and that's it. That's my contact information. If anyone wants to contact me afterwards,